Welcome all. This is a theoretical computer science seminar at Jagiellonian. We're happy to have here today Marcin Pilipczuk from Warszawa. Marcin is an expert in algorithmics, specifically in fixed parameter tractability, in exact computations of hard problems, and in structural graph theory. Thank you for joining us, Marcin, today. The floor is yours.
Thanks for the invitation. So I'm going to tell you about my recent work with Roman, which happened when Roman was in Warsaw for internship last spring. And it's about scatter dimension and sparsity, but sparsity in metric space, so in graphs with edge weights, not the usual sparsity. So let's start with a bit of motivation. So let's go with the K-center problem. So K-center is a problem in metric spaces. So we have got some metric space, and some of the points in the metric space are clients. So this is a discrete metric space. Everything will be discrete today. Some points are clients. These are the circles on this picture. And some points are potential centers. And there's some budget, how many centers we can open. We're going to open some of the centers. So that means we're going to select some of the squares, be colorful. I put them red, green, and blue on this picture. And then the centers will serve the clients. And what we are going to optimize, what's like our cost, is what's the furthest distance a client needs to travel to its center. So what we are really doing, we are taking to every center, we are assigning every client to the closest center, and then we are looking who needs to travel the furthest, and that's our cost of the solution. And so in this picture, if we choose these three centers, then this guy, I think, in this picture has got the furthest distance, and this is like the cost of our solution. Right? So we can measure this. This is one of the clustering problems where you're like trying to partition clients into clusters and serve them somehow. And this is some sort of extremal one when you're measuring by the worst unhappiness of one of the clients. Right? And there's one of the classic algorithms how to solve this problem is an old one. It dates back to 22 or 23 years ago, but Piotr and Badu. And let's try to do, it will be an approximate algorithm. So we'll be trying not to find an exact solution, but we'll be trying to find 1 plus epsilon approximate solution. So there's some accuracy parameter epsilon. We're trying to find 1 of epsilon approximate solution. And what we do, we start with any solution. So we start with something with like sort of like a local search type, but not really local search, some branching local search type algorithm. So we start with any solution. Here K is free. So we just take 3 centers. That may not be the best choice, what we start from. And then we are looking, are we good enough? So what we are doing, we are really not asking the question, what's the best solution, but we are taking some L, and we are asking, can we find the solution of cost L, or rather find the solution of cost 1 plus epsilon L, or refute the hypothesis that opt is the most L. So in a sense, there are only like n squared options for the final cost, because there's a number of different distances between points in this metric space, and we can sort of enumerate all choices, what would be the optimal cost, and then try to find 1 plus epsilon factor. Okay? And now what we're doing, so we are trying to look this, and then looking, is this a solution of cost at most 1 plus epsilon L? Well, on this picture, it doesn't look like, because there's actually this guy here being very far away. So we're taking one of these guys, and we are guessing, branching or randomly choosing, what would be his color, what would be his cluster in optimal solution, which of the 3, red, green, or blue, guys will serve this guy in optimal solution. So then we'll branch, and I will choose the correct branch. So this guy is actually red, if you remember the solution from a slide ago. So this guy is actually red, so we guess it, and now we recompute where the red center is. So now we guess this guy to be red. We have 1 more guy colored red, 1 more client that wants to be served by the red center. And now we are solving locally a 1 center problem for the red guys. Yes, so we are looking at the guys currently colored red, and we are choosing the optimal guy for him, because that's a polynomial dimensional problem. That's inspecting all the potential centers and choosing the best guy for the red clients. Okay, and continue. So now this guy becomes a center. Oh, maybe it's not the optimal, but it's good enough because we want to be with an R, within this as L. Then actually it turns out that this guy is far away. So you recompute the blue center, and you move it here. And now, actually, this is still not a good solution because now this guy is too far from his closest center. So now you guess that he's green, and you move the green guy, but you move the green guy now to close because now this guy is unhappy. This guy is too far from the green center, but he's in optimal solution also green. You guess that this is green. That's branching step, and now you need to serve these two green guys at the beginning. So this is probably the best way to serve them with one center is actually this guy, and this is finally good solution. It's actually the optimal solution you can see on the first slide. That's sort of branching algorithm. It looks like when it finishes and says I'm fine, it really finds something, just verifies it. It really finds something with 1 plus epsilon factor of L, what it got at the beginning. If at some moment it decides that this one center problem is solving, so it gets some number of, say, red guys, and suddenly there's no center serving them within distance L, then it knows that it made either the guess of L is incorrect or one of the branches so far is incorrect, so it just terminates, says sorry, wrong branch. And yeah, so this is one of the branching algorithm that gives some solution. And the main question for the efficiency of this algorithm is how long it can process. I mean, how long this jumping, next guy, no, go there, go there, go there, happen. So let's try to bound this. So let's look how many while loop iterations we can have in this process. So let's fix one color. So let's say we are looking at the blue center only, and the guys guessed blue and the center moving. So at the beginning, the blue center is somewhere, and at some moment there was some client that was unhappy, that was too far away from the closest center, in particular from the green center, it was too far, and we guess that it's actually served green in the optimal solution. Okay, so what the algorithm does, the algorithm recomputes the blue center to something which is within distance at most L from this guy. But then maybe somewhere later during the algorithm, there's another guy guessed green, guessed blue that was unhappy so far, which means that at this moment this distance was too far, which means that we need to compute another center Q3, which is within distance here. This and this is at most L. This green dashed arrows at most L, and this continues and builds this type of structure in the metric space. So we have got these pairs of center and the next counterexample, the next guy guessed blue that's too far away, and we compute the new center. So we have got this structure when the guys in the pairs are further away than 1 plus epsilon L, and the guys on the green diagonals are within distance L from each other. Okay, and what happened 20 years ago was some analysis about how to really choose in R to the D, how to really choose in R to the D the centers Q1, Q2, because if you're solving a problem in R to the D, you're really having a continuous problem, and you can put the center somewhere. So there's really some argument how to choose the centers, consecutive centers, so that this is bounded in a Euclidean space. But what happened last year at FOCS was this many authors' paper, including some of our friends from Wrocław, that says that actually if you look at more heterogeneous metric space like graph with edge weights, then actually measuring what's the maximum length of such subsequence in a graph is actually a very good invariant of the quality of the metric space. You can think of this as like an invariant that for some classes of metric space you prove that this is small, and then you have a guarantee that some class of algorithms run fast of this metric space because you cannot have too long this type of structures. Okay. Yeah, and they call this epsilon scatter dimension. So this is what's called a scatter. This structure is called a scatter or epsilon scatter because it's parameterized by epsilon. It's like for some L happens, it's parameterized by epsilon, and the dimension is sort of how long you can build this structure. Okay. So let's look what are the easy bounds for epsilon for scatter dimension. And if you look at this, if you look at the first two steps, then a triangle inequality shows you that actually here you have got more than epsilon L between these two guys, yeah, because this one is at most L, this one is larger than 1 plus epsilon L. That means that here you need to have at least epsilon L, otherwise the triangle inequality will violate. Okay, which means that if you look at the long ladder or long scatter, then actually these guys at the bottom, they're actually pairwise within distance at least epsilon L from each other. And I will call this a nomenclature coming from sparsity. A set of points is something scattered if the pairwise distance is more than the sum. That's the notion I will use both for the metric space and for the graphs. Okay, so these points So you can think of the last guy not really present there, because in the algorithm you're not really finding the last guy, so you don't care about the last guys. But the remaining guys are epsilon is scattered, but they're all served by this guy. Yeah, the algorithm still found Q6 that was the solution to the one center problem for the blue guys. That means that all these guys can be served by a single center within distance L. So we have got many guys, 5 here, which are epsilon L within distance from each other, but they're all hidden in a ball of radius L from the last guy. So now if you know the notion, which is quite standard notion of quality of metric spaces, namely doubling dimension. Doubling dimension is how many balls of radius R½ you need to cover a ball of radius R. Here's the definition written. It's really like the logarithm of the number, so that it more or less coincides with the Euclidean dimension in the Euclidean space. So this is how many balls of smaller radius you need to cover double the radius, ball of double the radius. And now, if you look at this, if you look at this definition, then it's easy to see that you cannot find too large epsilon L scattered set in a ball of radius L, because if you have a ball of radius L, you cover it with constant number of balls of radius L². Then these are covered with constant square numbers of balls L over 4, and you go down to epsilon half L with this, and you can have only one pi in a ball of radius epsilon half. And you get sort of this type of bound on how long is this scatter in bounded doubling dimension. And bounded doubling dimension is sort of like the analog of sometimes a bounded degree from the graph fix. This is like the analog of or Euclidean space. This is well structured, or the things that behave like Euclidean space are metric space of bounded doubling dimension. So it's good that our things works easily for bounded doubling dimension. This is a good check that this is something nice or something that behaves well. Okay, so this paper introduced this definition, recognized that this is actually an important invariant. And what I think is the main contribution of this paper, apart from the definition of the scatter dimension, is that they actually solve much more than case center using just the fact that there's a bounded scatter dimension of the metric space. So what they showed is that if you assume that the metric space has bounded scatter dimension, then there's a fast generalization of the algorithm I showed you. This is the simplest case, but you can solve a median and many different complicated norm clustering problems using this approach with a few other randomization guessing tricks up there. And the only thing you need from the metric space is the assumption that the scatter dimension is bounded. This is like the only primitive you're using there from the metric space. Okay, so that's what they're doing there. And so they also analyzed how it works in R2D when it's something slightly different. There are long scatters in R2D, but you have the freedom of choosing continuously the new centers, and then you can prevent having long scatters up there. And but they also look at the graph metrics, which is really interesting for us today. And what they look is that they observe that if the graph inducing a metric has got bounded treewidth, then they have a complicated proof giving a double-exponential treewidth bound. And they also gave a very, I call it here absurd, but it's like a very complicated around proof that planar graphs have bounded scatter dimension by using a very complicated embedding theorem into graphs of bounded treewidth for planar graphs, and then going through the treewidth bound planar graphs and getting a very complicated bound for planar graphs for bounded scatter dimension. So this indicates that something happening here, but this really didn't look like the correct or the final or the nice proofs of these facts. So we looked into this with Roman, and our insight was two-way. First of all, is that this picture of scatter looks something very close to something what the model theory or like structural sparsity guys are calling semi-ladder, which I will introduce in a moment. And the second thing was the intuition that the bounded treewidth proof looks like sort of like how you prove uniform quasi-wideness or weak coloring numbers bound for bounded treewidth graphs. And it sort of uses the same type of tricks or the same way of looking at bounded treewidth graphs. And that was our insight. And what we really did is we really developed some sort of metric analogs of my sparsity invariant, metric mean or closed graph classes, and showed that actually the well-established now pipeline, how you prove sparsity bounds for minor closed graph classes, actually once you understand what are the correct analogs of the definitions in the metric spaces, then all the proofs with minor adjustments just copy paste and here now. So let's try to go over this tool, how it works. Okay, so just to be on the same page, I know that I have got here in the room and probably online many experts in sparsity or even bigger than I am. So what we can have here is that you have the theory of sparsity introduced by Neshetter and Sean de Mendes, which is a theory of structured graph classes well beyond planar graphs or well beyond exclusive minor graph classes. And if you look at them at the first glance, they're focused on solving, or from the algorithmic point of view, they're solving and focused problems which are about unweighted graphs within constant distance. They're really, once you look at them, you look at the first order model checking, so that you're looking at some formula expressed as first order logic, so you can quantify over individual vertices, but you can check adjacencies, but you cannot quantify over sets or bigger structures. And for example, in this language, you can express k-center for constant number of centers of constant radius, which sounds very restrictive, but that's how you can solve here. And this theory is really developed, and in very wide classes of graphs, you can actually solve efficiently or evaluate efficiently a full formula. Okay, and they have got wide scope of graph classes, and there is very rich toolbox established so far. And I would say we have got, thanks to also some papers originating here in Krakow, we have got a very good understanding of how it works in minor graph class. We have got quite a number of tight bounds on many objects there in minor closed graph classes. We have got some sort of clean proofs how it works in minor closed graph classes. So let's go to the semi-ladders, which is like the first anchor here. So for that, we'll need to fix some FO formula, which takes two variables. But you should think about the formula that the distance between these two guys is at most d for some constant d. This is easy to express in FO. You quantify over intermediate vertices and say that there's a path of length at most d between x and y. Excellent. And now a semi-ladder is a sequence, as before, of q's and p's. But now on the green diagonals, the formula is satisfied, but on the red ranks of this ladder, the formula is not satisfied. Okay, so this is how a semi-ladder looks like. So if you think of formula distance at most d, then this is really a scatter for L equal d and epsilon smaller than 1 over d. The distance here is at most d, and the distance here is larger than d, or if you have an unweighted graph underneath. So this is yes. So this is how it works. So this is like how a ladder works, and this is like the semi-ladder like looks. I mean, there's defined for any formula, but we'll be focusing only on the formula being distance most d, and this is exactly like, or it looks almost like a scatter for some specific set of parameters. Okay, so there's actually proofs why for this formula phi, why there are no long semi-ladders next to minor graph classes, and it goes through 3 steps. The first step is to actually understand how something called weak coloring numbers, which some of you know, but I will introduce in a moment, look in closed graph classes and how you actually provide good bounds for them. And the tool you use here is something called Cobb decompositions, which I won't talk much about, but there's a tool for that. Then using weak coloring numbers, there's an elegant proof going to uniform quasi-wideness, which is another invariant from sparsity. And having uniform quasi-wideness, if you look how to bound the length of the semi-ladders, you realize that this is like the standard application of uniform quasi-wideness. Like the uniform quasi-wideness was born to provide such proofs. This is like exactly the correct tool to prove such things. And I will show you this proof later during this talk. So now we are going to look at this pipeline and see how to correctly project it to the metric case, to the case where there are edge weights and we're looking at the graph metric space on an excluded minor graph from some K8 minor figure. Okay, so let's go to the weak coloring numbers. So here we have a graph, and we are evaluating like a decomposition is an order. So we are having some fixed radius d, so some fixed distance we care about d, and we are taking an ordering. So our notion of decomposition is an ordering. And now what we want, we are measuring whether one vertex is weakly reachable from another one, which means that we start from the Vj, here V5, and we can go by a path of length at most d, and the endpoint needs to be the leftmost vertex of the path. So the things where we are ending, or the things we're reaching for, needs to be the leftmost guy on the path, which means that this is really a path in the graph induced by the vertices later than the guy we are aiming at. Okay? And now what we are trying to aim, we're trying to make an ordering where every guy has got a small number of weak reachable guys. So we are minimizing how many, the maximum number, how many one guy has got weak reachable guys. And you can think that for d equal 1, this is the degeneracy ordering. So for d equal 1, you're really measuring the number of left neighbors, because the guys weak reachable are just direct left neighbors if you measure a path of length at most 1. And you're really taking a degeneracy ordering, so this is really a generalization of the degeneracy ordering. Therefore, constant small distance. For constant distance. Okay, so this is how it goes. And copy decompositions. This is something which is known and established, so I don't want to talk. I want to go to our own proofs, which are later. There is it was coined for some completely different purpose, namely for a game when some cops try to catch a robber in a graph, and cops have got speed 1 and robber has got speed 1, and they try to catch each other. So a cop can guard a geodesic in a graph from a cop, from the robber. And there was a way of showing that in next Ka version of 3 graphs, roughly h cops Kh are okay. And some time ago, we realized this is actually a very good way of actually providing the strategy for the cops actually a very good way of providing good weak coloring orderings for these guys. And we have got bounds roughly looking like this. I didn't copy it exactly, but there are sort of exponential in h and polynomial in d here, what you get for Kh minor 3. So now the question is, how do you want to generalize it to metric spaces? What's the correct thing? Because this looks like looking for an unweighted constant distance. And the correct insight is that you want not to think about individual vertices, but you want to look at small subgraphs of a vertex is a small subgraph of diameter epsilon L. So in a sense, the vertices stop to be single points. There are small pieces, like small diameter pieces of the graph. And how we realize that what provides us the proof is that what provides us with the tool is that actually on last SODA appeared something called buffered decomposition, which is like this tool that was used here, but the paths are somehow buffered. There are some buffers they used to solve other problems, some problems, provide some other problems, but they develop sort of like a metric analog of the Cobb decomposition, where there are some guarantees about some distances in the decomposition, which I didn't tell you about. But what we observed here is that if you take buffered Cobb decomposition and use it instead of the normal Cobb decomposition of the weak coloring numbers, you get actually this form. You get this form of the weak coloring numbers, and now let us spend a few minutes on deciphering this full slide of definition. So what we are having here, we are having a graph with edge weights, and now we are giving not one distance, but we are giving two distances. We are giving the radius we care about, and the tiny radius, which is something like the error we are fine with having. This is like the error radius here. So what we are doing, we are computing a partition of the vertex set. So we are splitting the graph into clusters or small clusters, blobs, small blobs. And these blobs are tiny. These blobs have got strong diameter rho. So they have got really tiny diameter. So there are many tiny pieces. Think of like some small pieces. And you are ordering these pieces from P1 to P8. So these pieces are like vertices. So we're partitioning into these small pieces, and you're ordering these pieces such that, and now within distance R, the weak reachable sets are small. What does it mean? That means that if you take one of these pieces and look, who can you reach within distance R without going to an earlier blob? So you again can have a path that starts in any vertex here, ends in any vertex here, and goes somewhere through some of the blobs. But the distance at most R, and the final blob is the leftmost blob of the entire path that was visited by the entire path. Okay, so now this is now the notion of being weak reachable from one blob to another blob. and now we want small number of weak reachable blobs from one blob. Okay, and we get bound that's more or less resembles what was before. We call that before we had dh to the power of h. So now we have got and this is like the important insight. Now the role of d is overtaken by the node by the ratio of radius. So now we care about radius r, we care about distance r, and our blobs, so our instances error bars are rho, and the distance, I mean the things like it's more and more difficult. The bigger the ratio between r and rho is, the more difficult it is, because we have got tinier pieces and longer distance, and that's why like the ratio of these two distances came into play here as a parameter in the quality of the.
What is the strong parameter again?
It's like within the piece. So if you have got a graph and you take some piece within the graph, you can think of the diameter that takes into account paths going outside, or the diameter that's the diameter of the induced subgraph of this part. And the strong diameter is the stronger one, the diameter of the induced part. So you can have either the maximum distance between the vertices, but the distance can go outside the piece, or you are measured, or you can need to stay inside the piece. Yes. So this is like better. Better. But actually, all our usages will be fine with weak diameter here. So I'm not sure how important this strong. I put it here because we can obtain it, but I'm not sure how important it is. I think all our applications that we know actually are happy with weak diameter.
So here those blobs are like contracted. You contract them into a single vertex, and then you would follow this path.
No, they're there. So this path can travel through the blobs, and it's actually, it pays for traveling through the blobs.
Okay, so distance at most r is
including going through the blobs. I'm not contracting them. So this is really like, I'm looking at, so I'm saying that the blob P2 is weakly reachable from blob P5. If I look at the induced subgraph by all these blobs here, and the minimum distance between a vertex of P5 and the vertex of P2 is less than r, or at most r.
So you are allowed to to enter those blobs multiple
yes.
times.
Yes.
And by so you are discounting those that you can kind of reach, which is like the part that you hit is the leftmost of the all.
Yes.
So it doesn't count if you've been there before in some other vertex.
I mean, I'm counting number of blobs, so I don't understand this question. I'm counting how many blobs I can touch.
Just touch.
I mean, have any vertex in.
So it's not that it must be leftmost along the stuff.
No, it's the left. I mean, so I'm saying that. Okay, so let me take this definition fully. I'm saying that the blob, this is Pi, is weakly reachable from the blob Pj. If there is a path from any vertex of Pj to any vertex of Pi, that's completely contained in the blobs to the right of Pi.
Except the last one.
Yeah, except the last vertex.
Okay.
Marcin, can I ask a quick question?
Yes.
So what's the most general graph class in which you expect such a theorem to be true if you just ask for any function of rho and r? So any bounded expansion class would work?
I don't have a formal proof, but my intuition is that these questions get very strange if you go beyond minor code graph classes. In a sense, when you look at the metric space and you're fine with putting weights on edges, any weights on edges, like and look at the structure of the graph, then the operation of taking a minor, or actually the opposite operation of subdividing an edge or replacing an edge with a small grid or a vertex with a tiny grid with tiny distances, is a very natural operation that shouldn't change, but that means that shouldn't change anything, but that means that you want to work in minor code graph classes. So in essence, I struggle to define the correct notion. I mean, you can phrase these problems, but somehow like problems become strange once you go beyond minor code graph classes. So I really didn't investigate it beyond minor code graph classes.
Okay, thanks.
Okay. Okay, so this is up there. So yeah, we have this, and it was almost for free. I mean, not really. I mean, the main weight or the difficulty here lied in understanding that we are actually having not vertices, but we are doing small parts, and we are providing it some partition and some parts. And once you understand that this is the statement you want, then actually taking buffer to complete composition, understanding how the previous proof for complete composition works, it sort of works. There are some small technical problems to solve, but it sort of works naturally as you expect. So these are weak coloring numbers. Let's go to uniform quasi-wideness, which is another tool that was used heavily in sparsity. So now we've again fixed some radius. We had a d before, now we have another d. And now what you want? You have got a graph. Here I draw this wheel because that's an excellent example. D will be 2 in our example. And you highlighted some vertices. A is the set of highlighted vertices. Here there are these blue squares are the highlighted vertices. And now you want to select a subset of the blue vertices that are pairwise far away from each other. They're descattered, so the distance is more than 2 between each other. And here you cannot do it because whoever 2 guys you choose, there's this connection through the middle that is of distance 2, and every 2 guys are of distance 1 or 2 from each other. But what uniform quasi-wideness says is that actually you can find a large set once you delete a few vertices. So what does it mean? That means that I'm allowed to delete a few vertices and then select a set that discovers here. And inside this wheel, it's very easy because once you delete the center, you're left with a circle, and now selecting every third vertex of this circle gives you a 2 scattered set. Remember that descattered means distance greater than b. Okay, so this is uniform quasi-wideness, and this is another property that's common to all the sparse graph classes, structured graph classes that sparsity is studying about, that this actually happens. And now I have wrote here the formal definition, which is like probably the definition that still makes sense and uses the highest quantify alternation in graph theory. And everybody who sees for the first time is scared of the quantifier definition. But let's decide, because the quantifier order will actually be important here. So here we fix the radius. And the number of guys we'll be deleting, as will be the number of guys we'll be deleting, it depends on the radius. And this is important for uniform wideness. We're deleting 1 guy regardless of the length of the cycle. So there's only a constant number of guys depending only on the radius, how many guys we delete, such that for however guys we want in the end, there's some number of guys we need to start from, such that for any graph because this is a property of graph class. So uniform quasi-wideness is the property of the graph class. So for any graph from the graph class, however blue guys you choose, if you choose enough blue guys, then there is a small number of guys that you want to delete, and inside the rest you can find a good descatter set that's large enough. Okay, so that's how the uniform quasi-wideness works. So there's a small number that depends on the radius guys you kill, such that you can, in a large set, in a huge set, you can find a large descatter set after divisions. Okay, so now, how uniform quasi-wideness would look like for metric spaces. The point is that there may not be, like deletion of a single vertex may not change much in a graph with edge weights, because essentially every vertex can be really a small grid with tiny distances connected to outside, and deleting a single vertex from this grid doesn't look like a progress. Like every edge could be actually like a tube, a long grid with small distances, so deleting a single vertex doesn't make sense. What we want to delete, we want to delete subgraphs of small diameter, we want to delete small balls. That's like the deletion object we want to say. So now if you have got this uniform quasi-wideness that I showed you on the previous, and this is like the formal thing, and what I want to say that there is a simple proof that we developed with Wojtek and some other authors a few years when Wojtek was doing his master thesis. We developed a simple uniform quasi-wideness proof from weak coloring numbers, that if you have got weak ordering with weak coloring C for radius D, then there's a uniform quasi-wideness with C deletions and this number of blue guys to get M guys out of it. And we actually had a lower bound that this is more or less tight dependency in H minor 3 graphs. So this is the correct proof for minor 3 graphs classes up there for minor 3 classes. So in metric UQ, what do you want? You want to first delete balls or delete graphs of small diameter, and second, you need to start with a set which is already somewhat scattered. So if you have got a lot of guys but super close to each other, there's little chance you will be able to put them far away from each other. I mean, if you have a grid with tiny distances on the edges and a lot of guys up there, then to cut them into scattered sets, you would need really to isolate the guys. make a divisions comparable to the size of the set you want to do. So what you want, so metric uniform quasi-wideness is really about taking scattered set and making it more scattered set, like increasing the radius of the scatter. So you're starting with a set which is rho scattered, and you're going for a set which is r scattered up here. And you're deleting balls of radius rho. It turns out inside the proof that this rho and rho could be the same or could be close to each other. It doesn't really matter. It's some small radius. I don't think there's anything trying to distinguish in these two distances up here. And what we really observed is that once you get the understanding that this is the definition you want to increase scatterness of a set, and you want to kill balls of small radius more or less the same as the original scatterness, then actually you take the proof we had with Wojtek and others a few years back, and you copy-paste using the new weak coloring numbers. And you get the new proof with more or less the same dependencies. Now, if I put here f, because the formulas gets complicated, but now you should take these numbers here and put this c being r over rho times h to order of h from the previous bounds, and you get, and you put these numbers here, and you can see that this will be single exponential in h, this will be double exponential in h, and you get these numbers. But also like the uniform quasi-wideness previous, the lower bound also holds here. Essentially, you cannot get better metric things because this non-metric thing is actually a bit simpler than what you get here. But yeah, you get this metric uniform quasi-wideness here. So I didn't show you the proof because the proof is just copy-pasting the proof we had a few years back. But now I want to show you the proof because now I want to show you why uniform quasi-wideness is the tool born to prove that the scatter dimension is bounded. So assume that we have got metric uniform quasi-wideness, and we have got a long scatter. Here on this slide, long means 10, just because this fit on the slide. But we have got the long scatter, and now we want to use uniform quasi-wideness to say that actually it can be too long. So remember that we have proved that these guys, except for the last guys, are epsilon alpha scattered. These guys are epsilon L scattered. Okay, scattered. That means that this is the guys we want to use uniform quasi-wideness for. Okay, so we want to use uniform quasi-wideness for them, but for what radius? And now the intuition is that they're all within the ball of radius L from Q10. They're all within this ball, so this means that their pairwise distance is 2L from each other, which means that we want to make them 2L scattered. We want to increase distance beyond 2L, so that this constant number of red balls will actually need to hit all these green connections here, or most of these green connections here, and somehow establish the intuition that in a sparse graph class, this green connection needs to go through the same highway. They need to go together. They cannot be like somehow very complicated. They just need to go together. So we're using for the PIs, we're using the metric uniform quasi-wideness for rho being this, because I scatter, and for radius, the target scatterness is 2L. So what we get these 3 red balls, which are the deleted balls, the deleted sets. I put them on the side because if I put them in the middle of the picture, it would be too nice. And we had the green guys here, the green circles guy here, which are now 2L scattered once you deleted the red guys. Okay. So now you do the second thing, which is very common in uniform quasi-wideness. Namely, you sort the vertices according to the distance profile to the deleted set. What do I mean here now? So I now look at Qs. It will be more natural to look at Qs. I look at the corresponding Qs. And I look at the distance, say, look at this Q2, and I look at the distance to this set. What's the distance to this set? Okay? And I don't care about the exact distance. I care about the distance up to plus epsilon L additive error. So I care about like whether it's between 0 and epsilon L. I care whether it's between epsilon L and 2 epsilon L up here. And I don't care if it's more than 2L, I don't care. More than 2L is like infinite distance, I don't care. So there are roughly 2 over epsilon different distances I care about, like different brackets of distances. And for every vertex Qi corresponding to the PI I selected, and for every red ball, I look which bracket, which segment this distance falls in, and I classify these Qs according to this guy to all the red guys, which is constant number. Remember, this is a constant number depending on the ratio between R and rho, and this is like important thing, that the ratio between R and rho is 2 over epsilon. Okay, the ratio between the radius is 2 over epsilon. So we are classifying these guys according to this approximate distance to the red balls. And if there's a lot of these guys, so we started with a lot long scattered, that means that uniform quasi-wideness gave us a lot of these green circles. So there are a lot of corresponding QIs, which means, but there's only like 2 over epsilon to the size of S different approximate distance profiles, or the approximate distance vectors to S, which means that we can find a few of them with exactly the same. Or we can think that there are a few of them, say 3, Q5, Q7, Q8, which have got more or less the same distance to all the red balls. More or less, which means that there's some epsilon L error up there. Okay, so we have got these guys. And now, the observation now here is that, well, but now, these two guys, the two later guys, Q7, Q8, no, sorry, the other way around. Q8 has got P5 and P7 within distance L. Okay, so going here and going here, this is at most 2L. But after deleting the red balls, there are 2L scatters. This distance is more than 2L. That means that either this edge, this path, or this path goes through actually the red ball. So what actually really happens is that one of these guys, say this one, doesn't land here. It actually goes through the red ball. Okay, so one of the connections, one of the shortest path connections from Q8 either to P7 or to P5, I drew P7, but P5 would be analogous, goes through a red ball. Okay, fine. But remember that this Q5, Q7, Q8 had the same distance profile to the red balls, which means that now, but now if I go here to the red ball, this and this are roughly the same up to epsilon L error. This is roughly the same distance, which means that I could have gone to the red ball here and go here and get distance rough smaller than 1 plus epsilon L, which is a contradiction because that was a red rank which was larger than 1 plus epsilon L. So this is like this contradiction that says, fine, okay, what happened is that I said, okay, one of the paths from P5 to Q8 or P7 to Q8 goes through a red ball, say Q7 to Q8 goes through a red ball, okay? But now the distance from Q7 to red ball is roughly the same as Q8 to the red ball, which means that Q7 to P7 has got roughly the same distance, or smaller than Q8 to P7, up to epsilon error, and but that's a contradiction from there. I did some cheating. The epsilon doubles here. I needed to have it earlier and work with smaller. Yes. I mean, I added two epsilon. It needs to be epsilon half. I cheated here. There's some constants applying here, so that would have needed to have been a scatter for 2 epsilon, or I need to have the epsilon earlier. I cheated it just up here, but this is not really important for. I mean, this doesn't change anything apart from some constants. But the point is that this is a contradiction. There's this gap between distance L and 1 plus epsilon L, so that this argument is true. So the uniform quasi-wideness, really, this function capital M in the uniform quasi-wideness really governs how long a scatter can be in the metric space. And this is like the proof of the scatter dimension. This is like the proof of the scatter dimension that. I mean, I would say that this is like the canonical usage of the uniform quasi-wideness sparsity. How do you do that? You have a guys long sequence, you partition, you apply uniform quasi-wideness, and then you somehow classify the guys according to the distance to the deleted set.
So in the definition, you also read that the initial scattering was the same as the radius of the balls you're using. Yes, that was the key, right?
Yes, but I mean, that's roughly the same, but here I could like take epsilon over 3 and say that, okay, there are epsilon scatters, there are also epsilon over 3 scatters. So I would just have the ratio of the radii being worse and slightly worse bound for the yes. Yeah, I'm adding here, if you look at this proof, I'm adding here an error like this scatterness of P's comes from the difference between red and green. So that's one error I have. I mean, that's something I want to offset against. And the error comes from the error in the distance profiles that I do, which I have got some control about how fine-grained I am. And this error comes from the radius of the red ball. So I want the radius of the red ball plus my fine-grainedness error to be smaller than the difference between green and red arrows. There. Okay.
But the brackets was of size FCL, but then this bump from Q8 to P7 was of size at most FCL. So this is where
Q8 to P7 was at most L.
Most
L.
The blue one is at most L.
This one is at most L.
But it has to go through the red.
It goes through the red. That means that this one is only epsilon L longer than this one.
Yes. So it's 1 plus epsilon. Say.
I mean, I'm saying that difference between this one and this one is the error I introduced in this classifying of the distance vectors. And then I need to connect them inside the red. So I pay extra radius of the red to connect the x.
Twice radius.
Yes. Yeah, so I need to somewhere here have the epsilon to make the formal argument. Right. Okay. So we have got this, and we have got the scattered dimensions. So we have got like essentially clean. And what's important here is that because we can not maybe copy paste, but we can also use the lower bound. So there's a lower bound for uniform quasi-wideness, you just copy paste. And if you look at the uniform quasi-wideness bound, you can actually provide a scattered dimension lower bound for the tree graphs, proving that actually this the dependency you get here, which is like as you get, as you can remember, this was essentially this function m here, and this function m, this is essentially optimal. So we actually have a construction that is more or less, I mean, there are some slackness, slight slackness there, but this is more or less optimal. You will get the double exponential here. It's in some place here. But you can actually get this type of construction. And what happened later, which I want to say here, is that so we look at there, and what we realized later that actually Marek Sokołowski in his master thesis looked also at these ladders from pure sparsity point of view. So he defined this ladder for this FO formula, distance d, distance d plus 1, and he actually looked. He also had a similar lower bound for these ladders in the minor, and he also had an exponential lower bound for planar graphs. So after we had this paper, I was talking to Hongle, who asked me, can we get a polynomial bound to scatter dimension of planar graphs? What is the correct dependency of planar graphs? Because the lower bound really is not planar, it's really bounded tree lower bound. And we actually looked at realized later that there's a lower bound in Marek Sokołowski master thesis that shows that unfortunately there's an exponential, you can draw an exponential scatter even planar graphs. It's tricky, but it's quite not very complicated, but quite tricky how to draw it. Okay. So in some sense, we sort of understand what are the correct dimensions, what are the correct answers for the epsilon scatter dimension by connecting it properly. And I want to emphasize here that, like, I would say that the main, like, the most, I mean, not most difficult. I want to say that I would say that the main contribution is to actually understand what are the metric analogs of the definitions, and realizing that the clean proofs we have go through for the metric definitions. And actually, what we had was developed in the reverse order. We first realized that sort of uniform quasi-wideness type of statement we passed bound, and then we work it back in the order represented here. Okay. So what we have seen the definition of the metric sparsity, we have seen the weight coloring numbers, we have seen the uniform quasi-wideness, we have seen scatters, and they sort of like was, I would say, the correct understanding how they should work in metric spaces. And we have seen adaptations of known proofs from my approach. I showed you the last one, but the rest ones I didn't show you because they're sort of adapted known proofs from literature. And what this is the answer to the question we already discussed here. I want to emphasize here that I'm not sure what's beyond this theorem, what's beyond binary closed graph classes, because for me, while studying the questions, I have got some classes of graphs, and I'm studying all metrics for any weights functions on this metrics, on this graphs from metrics, then somehow being minor closed is not a very natural assumption, because minor closed contracting edge corresponds to putting a tiny distance or a zero distance on an edge. So somehow being minor closed is a very natural assumption, and I'm somehow like, I'm afraid to ask the questions beyond minor closed graph classes because I don't understand what are the meaningful questions there, but maybe I just not, I'm just not good at theory building here to understand what would be the correct answers here, what would be the correct questions here. And I would say that the proofs we get are elegant tight because the proofs we copy pasted from are elegant and tight. So we get elegant proof tight in the end. And another problem which I don't use, what I want to show is that we also analyze the case center problem and we provide a coreset. So what's a coreset? a coreset is a subset of clients. So I have got these clients, and I can find some subset of clients, call it D, okay, such that I can measure the quality only with regards to this clients. What does it mean? That means that for any solution K, like the quality, that means that the maximum over client, the minimum over guy in the solution distance from X to C. This is like the quality of the solution with regards to all clients. This is not larger than 1 plus epsilon, but only if I look at the important clients. Yeah, so I want to sub-select a set of clients such that these are the important clients. I only care about them, but I have the guarantee that if I properly serve them, then the other guys are only 1 plus epsilon less happy than this case. Okay, and in general graphs, it's not very difficult to provide an example that you cannot find any guarantees of how big coreset you can find for k-center, because there are some examples when you can necessarily to remember everybody, because everybody is wrong. For every choice, there's one guy being wrong. But in minor graphs, actually this cannot happen, and we have used these tools, actually inspiring but more loosely on known kernels for dominating set in sparse graph classes, and we actually provide a coreset for k-center, which is polynomial in k, but has got some horrible exponent depending on 1 over epsilon and the fluid minor. Okay, and actually, and how good it remains open, how good function can have here. So actually, I was asking the question, okay, but it's also interesting what happens for constant case, but larger epsilon, and what's the, if you want to optimize dependency on epsilon, not on k, what would be the answer? I don't know. That's something that's open here. And we don't know any, I mean, if there are more applications, do we just find the correct way of proving scatter dimension, or is there anything further beyond?
What is stage there?
Excluded minor, this is KH minor.
So was there no polynomial coreset?
I think this was the first coreset considered. I think the case sent. Okay, I'm not a guy where I'm sort of an outlier for the clustering community. I got the impression that the case center is sort of like the odd sibling in the family of clusterings. That there's like, you can prove many things for k-median, like LP clustering up there, and case center you really have a lower boundary expectation. Because of this max, because of this. There's in general graphs there's no coreset for k-center.
No, but you don't have a similar result from. My understanding was that
there are, but we are not. First of all, we don't know how to prove it our using tools, and there are known very good courses for k-median k-means that we cannot compete with. And I think, if I understand correctly, there's a very recent line of research that essentially gets like tied up to very tight factors for k-median k-means corsets and understanding how it goes, and very different technique come into play when you have got more linear or more smooth function as in k-median or k-median.
They also like polynomial or even better.
Yeah, they're very good, and but much more like sampling techniques come into play when you're working with them that don't work for k-center. Okay, and I think I can finish here because that's what I want to do, and I sort of showed you most of the things I wanted to show. So thank you very much.
Thank you, Marcin.